Here's the first video on the series on my channel about quantum mechanics, and I really wanted to start from the basics. There are a lot of videos on YouTube about the Schrödinger equation and solving the Schrödinger equation, but I wanted to give it a go and try to explain you how this all works. And I also want to do that because this is Feynman's technique for learning. And if I can explain something like quantum mechanics, or at least an introduction to quantum mechanics, then I'm sure that I understood those concepts well enough. And today we're starting with the Schrödinger equation. So let's see what quantum mechanics is all about. So I'm following Griffiths, by the way. It's an amazing book. It is an introduction. It is not an advanced quantum mechanics book, but it's okay for starting quantum mechanics. So this is the textbook I'm using for giving these kind of lectures to make these videos. So here's this Schrödinger equation. It might look intimidating at first because it's a differential equation, because there are derivatives of something called psi. Psi is the function we want to find. And it's a partial differential equation, because here we have a partial derivative, here we have another partial derivative. A derivative with respect to time, and a derivative with respect to space, a second derivative with respect to space. So it's weird at first. I mean, where does this equation come from? And why is it useful in the first place? Well, this equation is useful because everything in quantum mechanics, or at least non-relativistic quantum mechanics, is governed by the Schrödinger equation. So the Schrödinger equation tells us how psi changes and what is psi in a particular location at a particular time. And psi tells us information about the particles. And I'll explain to you what information that psi gives. Psi sometimes is referred to as the state of the system. So it basically tells us everything about what we care about the particle, the things we can measure of the particle. So is there any derivation of this equation? I mean, can we derive it from other principles or something else? The answer is no. Unfortunately, you might be surprised to hear this, or you may already know that there is no derivation to the Schrödinger equation, and you shouldn't be kind of sad about it, because this is the postulate. This is the thing we say we see it's true because we make experiments and they agree with our theory. And this is the point, the starting point. It's not something we can derive because, for example, classical mechanics is incompatible with what we see happening at a microscopic level. So we need something new. We cannot derive this equation from our classical mechanics. The same way we didn't derive Newton's first law. We just assumed it was true. We do experiments, and the results it predicts are true. So the theory works. And when that theory doesn't work, we have to use a new instrument, a new theory, and we came up with this. So there is no derivation, but I mean, isn't it weird that we are able to write down on a whiteboard an equation that looks like this, so complicated, and just by guessing? Well, no, there is a motivation behind the Schrödinger equation. So basically, I don't want to spend too much time talking about history, but what happened is that light behaves as particles, and many experiments confirmed it. And they really proposed that maybe also matter particles behave like waves. If waves, light in terms of wave of electrics and magnetic fields, behave as particles, probably also matter particles behave like waves. So To a certain extent, it worked. Bohr first started with this idea, and a lot of things happened. And they tried to find a wave equation, because if you want to describe matter as a wave, well, then you need a wave differential equation. So what Schrödinger did is take the wave equation for light and use the de Broglie formulas for expressing quantities that, wave quantities like wavelength and frequency in terms of position and momentum using the de Broglie formula. And he came up with this. And that is not a derivation, that was an attempt to build a new theory. And the theory is successful because we make experiments and it works. But we know that matter, at the end of the day, is a particle. When we measure a particle, we see it a specific location. It's kind of clamped in to a point. It's not spread like a wave is. So what is this so-called wave function psi we're looking for? Well, Schrödinger thought that the particle was spread throughout space, and when you measured it, it kind of collapsed to that point. And there were a lot of interpretations. There are several videos on YouTube, and also Griffiths talks about this. But at the end of the day, the interpretation that works is experimentally. And remember, what we're trying to do is to fit data with equations. Our goal is not to write down a beautiful equation, even though this is beautiful, but it is only to fit the data. We kind of look at things, we explore things, we make experiments, and if our theory agrees with the experiment, then the theory is good and works. It could be as complicated as you want, it could be as simple as you want it to be, but at the end of the day, what matters is the things that the theory predicts. If they agree with the experiment, the theory is okay. Otherwise, it has to be thrown into the bin, and it doesn't work. So we're trying to fit data, I remember about it. And the interpretation of this wave function is that it's square module squared, because psi is also complex. As you can see, here is the imaginary unit, so this is a complex differential equation. Interpretation is that the modular squared of the wave function, that is a real number. Remember, this is very important, because at the end of the day, what we measure are real numbers, not imaginary numbers. Represents the probability density of finding the particle, well, the probability density of at a particular point. And in particular, since this is a density, we multiply it by some interval of space, and we sum up all those probabilities for these infinitesimal intervals, and this represents the probability of finding the particle not at a point, but across our interval. So if we try to find the particle from A to B, then this interval here represents the probability of finding the particle between A and B. Why can't we just talk about the probability at a single point? Well, because think about the real line. There are an infinite amount of numbers here, so the particle might be here, might be on the number next to it. It's a continuous grid of numbers. It's not discrete. So the probability of finding the particle at a specific point, when you have in an interval an infinite amount of numbers, it's kind of impossible. So it doesn't make sense. In fact, this interval, if the two integration limits are equal, well, the integral is just zero. This is how we define probabilities. So what we're interested in is finding the particle in a region. And as you can see, this wave function tells us about the probability with this interpretation. And this theory is said to be non-deterministic. Or at least the wave function is completely deterministic, because once you know some parameters, I'll explain you everything in a moment of this equation, then you know what psi is. But psi doesn't tell you exact information about the particle. It tells you a probabilistic information about the particle. And this might seem disturbing at first, but it isn't, because for me it's also, it seems more plausible than a deterministic theory. Otherwise, in principle, you could know what I'm going to do in, for example, a week. And I'm comfortable with this. But remember, it doesn't matter. At the end of the day, we want to make predictions and agree with the experiment. So here's what's important. This is the Schrödinger equation. It tells us how the wave function evolves given this V. This is called the potential. And we have this interpretation of the wave function. Now, the wave function in the Schrödinger equation is this V. This is the potential from classical mechanics. We said that it has nothing to do with classical mechanics, but we still bring some quantities of interest, because at the end of the day, this is what, well, in physics, we can measure position, we can measure momentum, and all of that. And we know what potential is in classical terms, and this is our old potential. So this is an energy equation, but you'll discover it later on. This basically represents the energy operator, and this, let's say, kind of energy operator on the wave function is this time derivative of the wave function times I h bar. And now that we understand something on this Schrödinger equation, we want to tell two things about normalization, and then we'll come back to the potential. Something that's very important is to normalize the function. This means that when we integrate the function over entire space, we should get 1, because the particle has to be somewhere. The total probability of finding the particle in the universe, in the entire space. Now we're doing one-dimensional quantum mechanics, but over in the entire space, the particle must exist somewhere. And this is a condition we impose, that the probability of finding the particle across all space is 1, because we're not using percentages, we're just using probabilities from 0 to 1. That is much better, in my opinion. So this is a very important condition the wave function has to satisfy. But the psi is time dependent, and also square modulus is time dependent. And if this quantity changes, then also the integral changes. And this wave function is no more normalizable, because when we get a solution to the Schrödinger equation, we want the function to be normalizable, so to satisfy this condition, and we find a constant that normalizes the wave function to a particular value of 1. Let me show you one example. If we have the wave function that looks something like this, this is normalizable. It's, imagine that this is the square modulus of our wave function, and the area under this curve, so basically this integral, can also be kind of 10,000. The important thing is that it is a number, so we can also set this equal to 1 and find a constant that multiplied by our wave function gives us 1 as an area when we do the integral. So we want the wave functions to be normalized. But can this wave function be normalized? No, of course it cannot be normalized, because it goes to infinity, and it diverges its area. It's infinite, so we cannot. The area under the graph is infinite, so we cannot normalize it. There is no constant, so the multiplied by the wave function gives us a number. So we only want functions that are normalizable. And this condition also implies that the higher ordered derivatives of this function, so the first, second, and so on, all goes to 0 as x approaches plus or minus infinity, and also the wave function has to go to 0, as you can see from this example. This is logical, of course. And another thing that is not stated most of the time from the beginning is that the wave function is continuous. Now you might say, of course, it makes sense. A wave function with a jump discontinuity. Well, how can you talk about the probability? For example, the function had a jump discontinuity, then the probability of finding the particle in this interval would be weird, isn't it? But this is not why the wave function has to be continuous. This condition is just encoded in the Schrödinger equation, because this is a differential equation, right? So if we want this function to be defined over the whole interval R without exception, then the solutions that are functions covering all the real line have to be differentiable, of course, because here we have a time derivative, here we have a special derivative. We're basically looking at functions that are differentiable across R. And you might say, okay, this is trivial, of course, it makes sense, but what does it have to do with continuity? Well, we all know that differentiability implies continuity. You study this well-defined theorem in calculus, and since differentiability implies continuity, a function that is differentiable must also be continuous. And you have to bear this in mind because it's so important. So the wave function has to be continuous, and also its first special derivative has to be continuous, because here we have a second derivative, the derivative of the first derivative. So the first space derivative of this function has to be continuous. And this is a very important property. Now, there's something I haven't told you. When the potential is infinite, although the wave function is continuous, the first derivative of the wave function with respect to space, obviously, is not continuous, but only when the potential is infinite. But we'll see that in more detail later on. Now, before ending this video, I wanted to show another important thing. We said that this is time dependent, of course, because psi is also time dependent, and we want this to be always normalized. And my claim is, if this function is normal, this interval is time independent, and if I normalize this function for some time, for example, t equals 0, then it will always be normalized. This is my claim, and I'll prove it, and I'll show you that this is the way it works. So how can we do it? Now we're stumbling upon some mathematics. So the modulus squared is psi times its complex conjugate. Now, we want to find, this is time independent only if its derivative is 0. So we might take the derivative of this. And if we take the derivative under the integral sign, it becomes a partial derivative, because here we have a function that depends upon space and time. So it becomes a partial derivative, and I want to find this, the derivative of this. Well, this is simple. We can apply the product rule. So we have d psi by dt. I'm using this notation, that it's more compact sometimes, times psi star, and we have plus d by dt of psi star times psi. Now, okay, these are the wave functions. I'm not writing the integral. We'll just write the what's inside the integral. And here we have the spatial derivative. well, we can figure out what the special derivative is from the Schrödinger equation. So let's move this constant to the other side of the equation, and we get this. d psi by dt equals to, so we divide by h, and we divide by I, so we multiply by minus I. So this becomes a plus, and this becomes a plus h over 2m, and we shouldn't forget the I factor, d squared psi by dx squared, plus the potential, but we have a minus because we dividing by I, and we have an h bar here. Now, we want the same but for the complex conjugate function. So all we have to do is to complex conjugate each term. So this is d of t psi equals to, let's put a minus sign because we have a ni, h bar I over 2m. Then we have a minus I, and this becomes a plus. Oh, sorry, I forgot the special derivative. Psi is complex, so we ought to complex conjugate it. Dx squared plus I divided by h bar psi star. Now we can put this into our equation here, and we have this. So we have all of this. H bar divided by 2m d squared psi by dx squared psi star, because we're multiplying by this factor, minus I divided by h bar psi star, and we have plus this, so minus I h bar over 2m, have the second derivative, spatial derivative, the complex conjugate function. Then I have a plus I over h bar v psi star psi. Now, these two terms are equal and opposite, so we can get rid of them. Their sum is 0, and here we can factor out I h bar over 2m. I h bar over 2m, and here we have the second derivative times its conjugate minus the second derivative times the function. I forgot about the function. And we can also reduce this. We can pull out the derivative operator, and you can simply check that differentiating what I'm writing here gives you back the second derivative terms and the previous equation. So this is not something magic that doesn't work. Okay. But now we've done all of this because we have to replace this into our integral. And here we have a partial derivative. Here we're integrating with respect to x, and we're integrating across all space. Instead of putting minus infinity, infinity, I'm using this notation. It's more complex, I like it. So what we get is this evaluated on minus infinity and infinity. So this equals to I h bar over 2m, and we have the first term, this is the first term from minus infinity to infinity, minus the second term. Now, this is also from minus infinity to infinity. The important thing here is that we said that to be normalizable, both the first and the higher terms derivatives and the wave function have to go to zero at x minus infinity and x plus infinity. Otherwise, they don't have a finite area. So they have to look like a bell, because otherwise they diverge and we cannot normalize them. So this integral here, this derivative, has to go to 0 at x infinity and x goes to minus infinity. And as x approaches infinity and minus infinity, also the wave function and its conjugate have to go to 0. So this goes to 0 and this goes to 0. And we're left with it 0. But if the time derivative of our probability is 0, it means that the probability is constant. And if we normalize the wave function at a time t equals 0 or t equals whatever you want to, whenever you want to normalize the wave function, then it stays normalized for all times. And this is crucial. And if this were not true, it would have been a great problem, because we had to normalize the wave function continuously to have this condition satisfied. So that's all for today. I hope you enjoyed this video, and as always, subscribe to my channel. And also, this is a boring video, of course. Next video, we're going to talk about interesting concepts, and we're going to solve this equation for some potential, because it works like this. You give the the Schrödinger equation a potential, and you try to solve it. And we're going to see the infinite square well, and also the case of the finite square well. So I hope you enjoyed this video.